Hello, everyone. I'm Susan Nash, AAPG, and I'm delighted to be here today to welcome you to another fantastic AAPG Academy. Today's a little bit different than some of the earlier ones because we will have a panel rather than a one long presentation. So this will give you a chance to see some of the different aspects of petroleum systems, but we will follow up with longer lectures. It just depends on when there's availability. I'd like to mention that you will be receiving an email with a link to the recording. And so that will give you a chance to do the closed captioning. I will not do live transcription because it is not a very good thing for some of our people who have seizure disorders, and also because it also can be done after the fact in the recording. So I want to apologize in advance if you're requesting live transcription, but it will not happen in this one. And so anyway, I'd like to go ahead and introduce you to our presenters today. So we have our first presenter will be Sumit Mukherjee, who will be talking to us about petroleum systems and mixing of innovation and science. We have Zhiyong of ZetaWare and Jean-Marie Legel, Belmont Technology, and Craig Berry of Applied Petroleum Technology. So without delaying anymore, I'd like to turn the platform over to Sumit Mukherjee, and he will make an exciting announcement.
Thanks, Susan, and thanks to all of you who has actually joined the meeting. So the goal of today's meeting is actually threefold. First of all, you have seen actually there is a series of talks that's going to be presented, and as Susan actually mentioned in an earlier announcement that we are going to announce something during this presentation. So without delay, first, I'd like to thank actually AAPG for supporting and hosting a session dedicated to petroleum systems through the AAPG Academy. And thanks to all the presenters whom you're going to see talking about petroleum systems. My name is Sumit Mukherjee, and I'm a geoscientist by background. And as you can see from the title of the talk, it's pretty generic. It has threefold goal for this particular presentation. First of all, hopefully this presentation will pave the path to connect the subsequent talks that you're going to see today. The second one, hopefully you'll get to see an appreciation of uncertainty, because obviously in the subsurface, every time we look at data, every time we look at seismic to models, there is a huge amount of uncertainty, and we often don't appreciate the fact that we don't know a lot still in some of these basins. So maybe actually fostering that curiosity will come there. And third, we'll be actually making an announcement. Okay, so without delay, let me get into the talk. So curiosity, this is really a human inner trait. So we are always curious, and I just can't resist to show this chart. Obviously, oil price is a hot debated topic these days. And this is slightly old, it's from July. So as you can see, actually back in the July, we are around 60, just over $60 or so. And even then, it didn't stop us to predict or be curious where the oil price will go in a year or two post-COVID. And obviously, because as human beings, we are curious, we wanted to do innovation, and obviously there is a lot of modeling been done, and we predicted with an uncertainty outcome of the oil price. And we all know actually oil price probably has increased since that day. So definitely we practice our curiosity and innovation on everyday life. Now, if you take that curiosity mindset and put it in a shoe of geoscience, we probably have taken the curiosity probably in a different dimension. We not only are curious on present day, but we look back through geological times and try to understand the Earth's history through geologic time. And since today's topic is mostly around petroleum system, and geoscientists are always curious about learning rocks, so being a petroleum systems and putting that shoe, let's look at source rocks. So if we look at source rock, what we see on the right-hand diagram is obviously the source rocks are present throughout geological history through distinct geologic time frame. And what we see on the right side, there are two particular geological time where the source rock are really present in a voluminous amount, which have resulted in producing significant amount of petroleum throughout across the globe. Now, the curiosity hat is, so what are the characters that makes these two distinct time frame really prolific for depositing source rocks? So on the top, what we are looking at is a Jurassic time slice from Blakey's map. And to the bottom, what we are looking at is a Cretaceous time slice of the source rock. So if you look at those two time slices, obviously there must be some geologic condition, either from tectonic, depositional environment, productivity, nutrient supply, which makes these two time slices really prolific to have deposited two of these distinct types of source rocks. So let's look at some examples, because these are really model derived data sets from seismic, gravity, from depositional understanding, from tectonic frameworks. So if we look at an example of the Jurassic time frame, there is a prolific source rock, which is the deepwater Tithonian source rock. We're going to look at some data around there. And obviously we'll look at the Cretaceous source rock, which is the Eagle Ford one. So on to the left, that's the Jurassic deepwater source rock. And for your reference, this is a generalized chronostratigraphy from GBDS. What we are seeing is obviously the early opening of the Gulf of Mexico, followed by the drift and the cooling, where actually the key Tithonian source rock have been deposited, followed by actually deposition of the multi-stack reservoirs in the Paleogene, Miocene, and younger intervals. And the basin has multiple seals. As a result, actually, it's a prolific petroleum systems. Now, to the bottom of this diagram, what we are looking at is a generalized cross-section going from shelf to the deep water part. And what we see, because it's a salt basin, so having traps is quite unique in this basin. So trap formation is quite widespread throughout the basin. Now, the key thing to look at it, if you look at the vertical scale, which is in depth in terms of kilometers, you can see the key source rock, which is that Jurassic Tithonian source rock, it's really deposited in a present day situation quite deep. Hence, we don't have access to that data, a lot of source penetration in the deep water part of Gulf of Mexico. We have very limited data sets. But if we look at, this is again a map taken from LinkedIn, which CGG actually has published. You can see actually there is a lot of fluids and rock data. So now if you look at the innovation hat, so obviously from the fluid understanding, we have actually built an understanding of the source rocks. Hence actually curiosity and innovation actually played a key part to unlock some of these potentials of these prolific basins. Now, if we switch actually from these conventional petroleum systems to the right to an unconventional petroleum systems, which is the Eagle Ford, again, it's a prolific unconventional place. And you can see because it's onshore and unconventional, so obviously there is a lot of drilling actually went into. So we have access to a lot of source rock data. But even then, having a lot of source rock data, we still can't actually get away from uncertainty. And I'm just showing one parameter. What we are looking at to the right is the TOC map, or the total organic map, carbon map of the lower Eagle Ford formation. So what we see actually, depending upon what kind of density or resistivity or sonic log we are using, we get to see a slight difference in the contour patterns of this TOC map for the same formation. So the key point here is, in one basin where we have very limited source rock data, obviously we live with uncertainty, whereas in another basin in onshore where you have a lot of source rock data, we still actually deal with a lot of uncertainty. Now, exploring that idea of uncertainty, it's not only actually source rock. When actually we are modeling a basin, we look at from a source kinetic perspective, source quality perspective, and obviously there is a big uncertainty depending upon how the basin actually has evolved, whether it's a passive margin or actually a reef basin. There is a huge uncertainty on temperature gradient. And depending on the depth of the source rock and the seismic quality, there is uncertainty on source depth, which results in an uncertainty in the maturity modeling. So you can see actually petroleum system can give us an understanding of these uncertainties, and it can help us to build actually an outcome which can be closely tied to the business perspective. So on to the right, you can see actually this diagram is taken from Sir Cabby's 2020 publication. Depending upon what kind of products we are expecting from a particular basin, it directly impacts the project economics and the rate of return, because whether it's an oil basin or it's a gassy basin, it impacts actually the rate of returns as a whole. So that's where actually petroleum systems, and you'll see actually the following talks, that understanding of a fluid becomes really important to unravel some of these basins from a business perspective. Now, putting the hat of innovation, since we are living in the age of 21st century, we can't actually escape from artificial intelligence. And there is a lot of publication nowadays we see in the space of artificial intelligence. And this is one such publication. And what this diagram is trying to show is, obviously, for understanding these models, we need to actually let the machine learn, and we need to have actually a representative geological model. And that representative geological model needs to be built with a good or a better understanding of the basin. As a result, what we need is a better geological knowledge and expertise on some key elements that will help us to unlock the potential and help us to define these more representative geological models. And we'll see actually again a talk around that in a subsequent presentation. So if we keep that theme in this talk, that obviously we need to explore the idea of artificial intelligence, but at the same time, we need to understand actually some of the inputs that goes into these models. Hence, I would like to take this opportunity to actually announce, actually with the help of AAPG, now actually we have established a technical interest group which is dedicated towards petroleum systems. The goal of this group, I hope, will be actually to bring and foster technical collaboration and probably bring some of the technical presentation and technical knowledge and advancement that we are seeing globally, and hopefully we'll be able to broadcast to a broader audience, and hopefully we'll have some stimulating discussion going forward. So this slide, for those of you who are actually practicing petroleum systems for a while, it's quite a simple one, but for those of you who are really new to this topic, what you can see from this slide is there are actually a lot of moving parts for petroleum systems. And it's one of the branch of geoscience which actually helps us to build an integrated understanding of the subsurface. And you can see it has a wide variety of application. It can be applied to conventional plays, just the one actually I've shown, Gulf of Mexico, but it can be applied really well into the unconventional plays like Eagle Ford, Bakken, or any other unconventional plays that you can think of. Not only that, actually, petroleum systems concept can equally be applied to new energy solutions like carbon capture and storage, and of course, geothermal. So in a nutshell, hopefully with the launch of the TIG, with the talks that we are going to see down the road later this year or early next year and so on, we hope actually this technical contribution through this group will be leveraged by the industry, academia, and in the scientific community to move forward the science to the next unknown. With that, I will end the talk, I think within 15 minutes. If anybody has any question, I'll be happy to actually answer or take any questions.
Why don't we save our questions to the end and we'll go on to our next presenter. That was really wonderful, Sumit. And I'd also like to take a moment to encourage everyone to join the TIG. So you will receive instructions on how to do that in the email. So so do you want to stop sharing your screen, Sumit, and we'll have.
Yeah, sure.
Okay, perfect. So we'll have our next presenter. So are you ready? So our next presenter is Zhiyong. Would you like to share the Zoom platform, please? Great. And also, I just want to thank everyone, and you'll be receiving an email with a link to the recording, and also that will have closed captioning. Wanted to explain also one reason we can't do closed captioning is because it also eats up bandwidth and crashes the entire program. So yeah, I don't know. We'll try. I'm working on that because we want to make accommodations for everyone. So Sumit, I'm sorry, Zhiyong, I don't think it's sharing. Here we go. Perfect. So I'd like to thank our sponsor, Aramco, and also like to thank IHS for sponsoring this series. And I'd also like to encourage everyone to be sure to renew or join AAPG so you can vote in the merger.
Should I start?
Yes.
Okay, great. Thanks again, Susan and Sumit. So this was my talk a few weeks ago for the London Geological Society meeting. My topic was top-down petroleum system analysis by mainly looking at petroleum phase, whether it's oil, gas, or both, and properties, right? So what kind of a GOR ranges are or API ranges are, that's going to be in your trap. And this was a 45-minute talk. Obviously, here I'm going to try to show just maybe 5 or 6 key slides from that. So as far as the oil versus gas, there's a pretty good settled bottom-up approach. If I may simplify it, is that the dominant phase in the basin is determined by the source rock. Okay, here I have 3. You can see 3 basins on this map on the left side. You have Nile Delta, which is pretty much 90% gas. Then you have the Gulf of Suez, which is pretty much 90% oil. And you have one that has both, right, 50-50. And that is the function of the source rock. Now, traditionally, we have always spent a lot of time doing basin modeling, trying to answer the maturity aspect of it. But, you know, we have oil windows and gas windows defined. And but if you look at basins over basins like this, it's pretty much all determined by, mostly determined by the source rock. You know, if you go to Nile Delta, I'm sure there's an oil window, but there's no oil, right? And you can go to Gulf of Mexico, there's a huge area of gas window, but there's no gas. So those they might have a secondary effect, but it's not the main effect. The main effect is the type of source rock. Now, once you get into a mixed basin, okay, basin with mixed oil and gas, the most important factor is also not maturity, and I'll show you why. Okay, here I'm going to show you a little video. This is how this is from Core Lab, and this is how we determine PVT properties of the fluids. Actually, it's how we determine whether it's oil or gas. So you're looking at cylinder. Okay, this is a little movie, so I'm going to go by going from high pressure to low pressure. Right now we're at single phase. This is actually oil. You know, this is gas. This is single phase oil right now. Okay, it's volatile oil, so it has dissolved gas in it. It's currently at 8,000 psi. Now, when you reduce the pressure from that, okay, so I'm going to move the cylinder is rotating away, so the volume of the chamber is expanding, so the pressure drops. And as you can see, nothing happens yet at about this point, 3,000 psi-ish. And look at the top. So the upper part is now the gas, and the lower part is oil. Okay, don't forget this oil still has gas in it, and this gas at the top still has liquid or oil composition type of things in it. And that's going to go on all the way pretty much to the surface. And this is what we get at the end, right? This is how we determine saturation pressure, which is the pressure at which the bubble starts to happen at the top, right? And if it starts at the top, then we call this thing oil. And on the other side, we'll see the gas. Now, this happens also to be what would be happening during migration. Okay, if this oil was generated at 8,000 psi, which is probably 4 or 5 kilometers, and as the oil migrates up to some shallower depths, you'll have a gas cap. Now, what's going to end up in your trap depends on what now. If put both of these things in the trap, if the trap is leaky, you might leak off the gas and end up being an oil field. And there will be certain properties of that oil. If this trap has a super good seal, then the oil might spill away and end up being a gas field. So this is what we think actually determines a lot of oil versus gas issues in these mixed basins. Let's look at the gas also. So we started at very high pressure again, same pressure pretty much in both situations. And as we decrease pressure, okay, as it happens during migration as well, when you move high gas in this case from deep to shallow. And this time we reach a point in pressure that's called dew point pressure. And now look at the bottom. Okay. Now the fact that this comes from the below, engineers will call this a gas condensate field, right? It's not actually the composition. The same composition can be an oil field, can be a gas field, depending on the temperature of the reservoir actually. Okay, same thing happens. Now you have liquid at the bottom and gas at the top. Again, if you apply the trap, if you put this fluid in the trap, and what's going to be end up in the trap depends on the seal. If the leaky seal, you have oil. If it's a spilling trap, you have a gas. So this is well written by John Sayles in a 97 paper in AAPG. I'd encourage people to look it up. It's called cost 1, 2, and 3. Depends on the seal. You can end up one phase or the other. Okay. I'll show you another observation. Globally, we find that if we plotted gas oil ratio versus depths, 90% of oils will plot in this cloud, okay? In which case the gas oil ratio increases with depths. And 90% of the gas condensate field plot in that cloud, in which case the gas oil ratio actually decreases with depths. Now, you might argue that could be a maturity fact, and I'm going to argue that's not. It's mainly still a PVT effect. It's a pressure effect. If you look at the gas side is the proof, right? You would say, you know, even for gas, the maturity should be higher at high GOR, but the high GORs are at the shallow ends, right? Well, there are several factors that go into this. We'll not discuss it. I'm going to say the main factor here is actually the pressure to determine this. This is from North Sea. You can see the gas oil ratios of oil fields are on here, and then gas oil ratios with gas fields are plotting along that line. Okay, and what's happening here, we think, is the principle, right? It's the underlying physics of that. Just like as we saw in the video, when you have certain hydrocarbons generated at depths and migrate to a shallow depth. If we start with, in this case, this is the orange color is gas condensate. It's mostly generated by a relatively gas-prone source rock, okay? And that fluid moves up to a certain pressure. This blue band here is actually the dew point pressure on the right-hand side, bubble point pressure on the left side. So when that fluid, which is gas condensate, reaches that point, you'll start dropping out liquid from the bottom. If the gas continues to move, because the pressure is lower, it cannot hold any more of that liquid. More liquid will drop out. Therefore, the gas oil ratios increase as it gets shallower. And you can say the same thing if you start with the oil. You may start with oil of 2000 GOR, but as you get to about 1 kilometer, the GOR will be less than 300. Okay, so up in this region, upper region of the basins, which is probably 80% of our field sits. And it's controlled, its gas oil ratios are controlled by PVT. Now, of course, you can generate a ultra low GOR oil, and it's going to stay single phase until very shallow depth, right? So that's why, if you look at the oil prone basins, we probably start from the green area and we end up very, very little gas, sometimes small gas fields, right? If we start from the right-hand side, again, it's the source rock that dominates which side you start from. You're going to end up with mostly gas fields, occasional oil fields from the liquid that drops out and, you know, we leak out the gas. How much time do I have, Sumit?
I think
2 minutes.
yeah,
Okay.
2 minutes.
2 minutes.
I'll give you one good example of that, okay? This is what we used to worry about, right? And this is the West of the Shetland Basin. If you make a burial history of it, you'll see the oil was generated in Cretaceous time before our reservoirs was deposited. Okay, the whole basin is super mature in the gas window, except the areas that don't have source rock. Okay, so the timing is way off. So what do we find in these traps in the reservoirs in the Paleocene, Eocene, right? And if you're looking at the gas window and the timing, you would say gas, right? And there's also volcanic, you know, activities that make it even more complicated. But if you go back to the two principles we talked about, first, well, since this is a very good oil prone source rock, I'm going to predict all the traps will have oil, which is pretty much the case. 90%, probably 90% of the volumes in this basin are oil, despite the whole basin being in gas window, despite oil was generated before the reservoirs was deposited. Okay, Now we do have some small gas fields, which we think is exactly what happens based on the other principle, which is that when the oil migrates to shallow enough depths, first you form a gas cap. Okay, this is the line that limits the GOR. So if it migrates further up dip, it'll be lower GOR. If you find something shallow here, it'll be even lower GOR. Now, when you have a gas cap, here's the sales model, okay? Which says basically you have a really tall trap, you're gonna leak off the gas and have oil fields. All of these are big structures, right? And they're all oil fields. Some have small gas caps. Okay. Now, if you have a small trap, what's going to happen is that when you have the gas cap big enough to fill it, then the oil has to spill. Then you end up with gas fields, and the gas oil ratio, or we usually say CGR, condensate gas ratio, is going to follow this trend. So that lets you predict gas oil ratios for the oil and CGRs for the gas. And the sales model can be used to predict whether you can have oil or gas in a particular trap. I think that's good. That's the key part of my talk. Hopefully this will make sense.
That's great. No, it's really good. And I'm just, again, want to invite any of the speakers to do to record a full one or schedule a full 45-minute one for sometime later, because these are wonderful. Anyway, so I want to welcome our next speaker. And if you'd like to go ahead, that would be great.
I'll stop sharing first.
Okay, Jean-Marie, that's great.
All right. Okay, I am Jean-Marie Legol. I am the CTO of Belmont Technology, and I have enjoyed very much your comments, Sumit, at the beginning of this session, where you were proposing a working group to integrate AI into the petroleum system world, and there are many components which needs to be involved in achieving this objective, but one of them is certainly to have a very fast inference engine. And this is what I'm going to discuss today in this talk. Machine learning represents a great opportunity to accelerate basin modeling simulation. In general, this is a very active research field, which is not new in itself, but which is gaining more traction in different domains thanks to the evolution of the framework and the hardware capability to train machine learning model. These are two article titles from recent publication, and there are many more about how AI has the ability to learn the solution of partial differential equation. And that's something which can be also achieved for the learning of the solution of the PDEs which are involved in basin modeling. I will show here an example of learning the solution of the heat equation with a couple of examples. So why do we want to do this? I think that one of the key benefits is that AI-based simulators are 1,000,000 times faster than conventional simulators. And when you have access to such a fast prediction engine, you can unlock new types of workflow. You can have access to solutions for interactive modeling, get instant results, which are absolutely similar to what you would get from a full physics simulator, but in seconds while you interpret or while you build models. Achieve an auto-calibration to every single observation and maintain evergreen models, perform high-resolution sensitivity analysis, or provide instant recommendation supported by concept, supported by knowledge bases, and also supported by physical insight. So I'm going to show specifically two examples today in this talk. One, which is STS maps from the entire Gulf Coast, which are calibrated automatically to 30,000 wells data. and another one which is a high resolution sensitivity analysis of erosion scenario in the North Sea. But before we go there, couple of comments on the concept behind training machine learning to learn the solution of PDEs and why does it work. Actually, we are here leveraging the fact that neural network can be a universal function approximator. This is something which has been demonstrated some time ago already, and there are examples of this for all of the different classes of PDEs. There is a being parabolic, which is the one that we are going to look at today. The heat equation is a good example of this, or hyperbolic or elliptic. There is a large corpus of bibliography showing the application of neural network to learn solution of PDEs for these different classes of equation. So what does it mean to train a machine learning model to learn the solution of PDEs for basin modeling? What we propose here is an end-to-end learning of the solution, meaning that we are going to shortcut the typical process, which consists in defining a geological model at present day, informed with lithologies and boundary condition, restore the geometry of this model through time, and then run it in a step-by-step manner to perform a forward simulation of temperature, maturity, pore pressure, and porosity, and so on through geological time. So we've demonstrated that neural networks have the ability to actually shortcut this entire process and learn an operator which make a mapping between description of a geological model and these properties from which example are provided by a numerical simulator. So that's a supervised learning. So it needs a data set of carefully chosen simulation examples. So I'm not going to expand today on how we generate this simulation example. In the frameworks that we propose, these are actually conceptual examples which are generated inside a framework. And when the model is trained, it can predict for any geological models that you would define inside this framework. So let's move to a first application of this. And this is a work which has been presented at the Digest 2021 conference in Norway earlier this year about performing a high resolution sensitivity analysis of scenarios around the glacial erosion in a certain area in the North Sea. There is a Plio-Pleistocene glacial erosion, and the timing is uncertain, the magnitude of this and the effect of this on the petroleum system is something which is poorly characterized. And that's a work which has been presented in collaboration with AAPG. So we have trained a model to being able to predict temperature and maturity in this type of geological setting, which takes in input a full description of the lithosphere, but also a fine-grained characterization of erosion in this area. This is actually quite a complex setting with two phases of erosion and a hiatus in between. And the total amount and how it is distributed within the two phases is something which is poorly constrained. So we have trained a model in this framework, and it has then been used in order to explore scenarios. So this is an example of what training a model look like. We generate, in that case, a large number of 1D simulation, which are conceptual example of possibilities inside this framework. So in that case, that has been 500,000 simulation example which have been used for training the model. It trains beautifully. The cross plots that you see here in the middle are presenting the comparison between the prediction by the trained model versus the values which are computed by a full physics 1D simulator for a data set which has not been used during training. So this is a blind test if you want. So you can appreciate the very low error that the machine learning model predicts, and the very nice distribution of this error. So that's something that it can be used confidently in order to predict for any geological model inside this framework. So when it is trained, we have access to very fast inference. So predicting temperature and maturity at a very high resolution at each location in this model is something which takes about 200 milliseconds and delivers at each location a prediction which is at 99% or more, absolutely comparable to what would deliver a full physics simulator. And that allows to perform, for instance, an interactive exploration of the model. So you can, for instance, decide to test different values for the radiogenic heat production in the upper crust. And the movie that I'm going to play shows 100 different prediction for 100 different values of this upper crust RHP, increasing it systematically. So you can have access to a slider which allows you to basically test different values and see the impact on the present day temperature or the present day ECRO or thermal stress, literally interactively. But we have also used this one in order to conduct a proper sensitivity analysis. And I'm going to show an example where we investigate 3 parameters. One, which is the total amount of erosion in the area. Another one, it is how much has been eroded during phase 1 versus phase 2, and also the duration of this glacial hiatus. So at one single location, if you want to perform a proper sensitivity analysis, you would need to run about 4,000 simulations. So given the size of the model, that's in total 3 billion prediction that needs to be performed to predict a map of the relative importance of each parameter, which is something not achievable with a typical simulator, but which is achievable with an AI-based simulator because of the fast inference. So this is a typical outcome of this process. It takes about 15 minutes when distributed on 96 cores, and show the maps of the relative importance of each parameter with respect to the present day maturity of the reserve formation. So that's a proper quantitative analysis of the influence of each parameter, which shows that they don't have an equal importance, and that varies depending on the areas. I'm not going to elaborate on the geological significance of this. I'm more here in order to highlight the process and the fact that getting this type of quantitative insight is something which is achievable today at a very low cost. Another example that I'd like to comment is how we can leverage an AI-based simulator to perform an automated calibration for a very large amount of wells. And in that case, this is more than 32,000 wells, which have been used for the calibration of temperature and STS maps in the Gulf Coast. And that's work which has been presented at the AAPG ACG image conference earlier this year with Andrew Pepper and his team. So we, in a similar fashion to what's been done for the Norwegian North Sea, we have trained a model in the geological context of the Gulf Coast with a certain number of assumptions given the size of the area. And we have been leveraging a database of 40,000 temperature records for the calibration of this model and the inversion of RHP values in the upper crust. So that's a process which takes only 40 minutes using an AI-based simulator that would have taken about 150 days with a conventional tool if you assume that a 1D full physics simulation would run in 10 seconds and using only 1 CPU core. So of course, not commenting here the speed of conventional tool, but an AI-based simulator is orders of magnitude faster, which makes it affordable in a very short time frame. So when this is trained, then you can access to prediction of properties at the scale of this model. And this is an example of an STS prediction, which honors the temperature data for more than 30 1,000 wells. And getting this prediction, so which is the equivalent of a forward simulation, at this resolution is something that takes basically 2 seconds. So we are really talking about interactive full physics prediction in this case. You can use a higher resolution map or update depths or lithological maps and still have access to this update at the same speed. And my last slide here is a movie showing the evolution of STS in this model, which is predicted by this trained simulator. Let you appreciate that evolution and the insights that it delivers, knowing that this is a result which is calibrated to every possible observation from this database. Yeah, so some concluding remarks here. It is today possible to train a very, very fast AI-based simulator. They are easy to train, and this is a process which is inexpensive, takes only a few hours of compute. This model and what I have shown today is still a multi-1D prediction, meaning that this is 1D prediction at each single location. We are working in making them full 2D or 3D, which is not particularly difficult from a technological standpoint. So the difficulty is more to have access to a good training data set. They deliver first order insights, which are absolutely similar to the one of conventional simulator, and they can predict for any geological model inside the training framework. And this unlocks a new type of workflow. So I mentioned interactive modeling, auto calibration, high resolution sensitivity analysis, or getting insight recommendation as you work, supported by concept and data. And I believe that they really empower geoscientists to integrate all data, rapidly explore scenarios, test ideas, and focus on the most impactful parameters. So this was this were example of thermal simulation that also can be done for pressure related properties, and that's the work that we've done as well. That's certainly something to be continued, but I believe that we are now at a stage where it can start being used more in operation. Thank you.
Well, thank you. That's been very impressive. And I would like to encourage you to participate in our program Energy and Data that we'll have in Austin. It will be a 3-day conference. So I'll send you more information. At the same time, I'd like to encourage all the attendees to keep your eye out for it. It'll be 3 societies. It's SPE, SEG, and AAPG. So I'd like to encourage everyone to check out the calendar and our upcoming events. And I'd also like to welcome Craig Berry of Applied Petroleum Technology to share the Zoom platform and to make his presentation on geochemical methods for production optimization. So welcome.
Thank you. Okay, so thank you for inviting me to present. And so I'm not going to be showing any models, but I will show a smidgen of geochemical data, certainly once I get through the presentation to the some of the case studies towards the end. So I'm going to be talking about production optimization and the opportunities that provides, as well as many of the challenges which arise in trying to get quantification and trying to understand what's happening in the subsurface. It is generally more complicated than people desire. And much of this work is by my colleagues, as well as conversations with others, many others over the last few years, particularly in the unconventionals. So when it comes to reservoir geochemistry, I'm really going to be talking about 2 things, which many people would be most familiar with. Production allocation, where you're assigning source contributions to clearly 2, being that you need 2 or more individual fluid sources at a particular point in time, based upon the fluid chemistry which you have. And then tying into that is production monitoring, where you're analyzing a time series of fluids from a particular location, so probably from a particular well. And what you're looking for are changes or otherwise in that fluid chemistry, and how that relates back to changes in source contributions or production related processes. Clearly, you can do both separately, but in most cases, you would want to do them together to get the most out of your data and to understand what's going on. Because you can just monitor a single well, but if you're just looking at a single well, then you are making a lot of inferences about why changes have perhaps taken place. And so this is perhaps most well known in conventional plays. And I mean, Mark McCaffrey did a huge amount of work up in the North Slope, and it's all to do with multiple producing reservoirs in the field, multiple fields under pipeline or multiple pipelines. And why is that? Because we want to understand source contributions and these fluid changes, quite often for tax purposes and various other items associated with that. And there's a whole body of work on conventional systems by many workers, Mark in particular. When it comes to unconventional plays, if we've worked in unconventionals, I mean, you're looking at distinct source and reservoir laterals and intersection of the fracs with potentially multiple source producing zones. Much more complex, although conventional systems are complex also, and a much larger range of deliverables. Everyone focuses on source contributions, but it must be borne in mind that that is only one deliverable. I'm going to hit that home as we wander through the presentation. DRV distribution, SRV compartmentalization, fluid variability, both laterally and stratigraphically, which can be quite difficult to get a handle on, saturation, mobility, all of these items from the geochemistry give a huge amount of understanding about your acreage, about what you're producing. And they're all a direct measurement of your fluids. So, I mean, perhaps one of the only direct measurements where you can get in there. So when it comes to production allocation and monitoring, there are challenges. And one of the overriding challenges is end member availability. If you're going to deconvolute fluids, then you ideally need the end members. Now, there are ways and means of doing it without having definitive end members, but it is preferred and you certainly have a much greater chance of success. But even if you have end members, you need to have end members which you can differentiate. If all of your fluids from your different zones are essentially the same, then you are going to struggle to differentiate and allocate from those results. And bear in mind that in many cases, you can see differences from a qualitative standpoint, perhaps a semi-quantitative standpoint. But when it comes to quantification and statistically separating out the fluids, it becomes a much larger challenge. And generally, all of the statisticians I have worked with have suggested that once you get beyond 4 or 5 distinct end members, you can't really separate out beyond that. And I'm quite happy to die on that hill. The other large issue is homogeneity. I mean, we assume from a conventional standpoint that generally we're dealing with homogeneity. That may actually not be the case. And in unconventionals, and we know for a fact that there is considerable lateral variation and heterogeneity. So how do we deal with that challenge? And then you have contamination, perhaps from OBM in your extracts, and then you have comparability. Extracted fluids are not produced fluids, so there are always differences that you have to deal with. But as I said, there are opportunities. As I said, most people think source contributions. That is one of the potential deliverables that you can get from this type of work, understanding directly what is contributing to your fluid that you are generating. You get a sense of compartmentalization. You can understand the extent of your drained rock volume, at least a potential extent of your drained rock volume. And you can look to understand parent-child relationships and whether you can add infill wells or whether you're going to have issues when you start to do infill. And then there's system trends. A lot of the work we do, certainly from a cuttings and core standpoint, is to understand what is the maturity trend, what is the facies trend across the acreage, and perhaps into other areas that the operators wish to target for the best production. I'm not going to spend a huge amount of time on this slide. Basically, what it's meant to emphasize is that there is no silver bullet. There is no one size fits all methodology. Why is that? Because the objectives of the operators are different. Every basin is somewhat different, and the phases which we are dealing with on projects can vary hugely. I've worked on some projects where I'm just allocating produced waters. At others, it's gases. In many, it's a combination of gases, waters, and oils. But those oils themselves can range from condensates to light oils, normal oils, or heavy oils. So there is a huge amount of variation. And so we would want to have a flexible approach. The vast majority of allocation work is done using gas chromatography. And it is probably by far the most robust approach. Seen plenty of work by Alan over the years on the light ends, and that is very, very useful for understanding your fluids, particularly in unconventional scenarios. But biomarkers hold their own, where you're perhaps dealing with more normal oils. And if you're going to work with waters or gases, then you're going to be looking at isotopes and composition. So just bear that in mind. You want that variability, and not every approach will work for every project. And you need reproducibility. If you're going to be looking at fluids across multiple years, then you need to understand what the error coming from the lab is on those samples 1, 2, 3, 4 years down the line. And finally on that, this should not be a black box. You should be able to take the solutions and the data you get and apply it to your own workflows. You should be able to understand what you're getting so you can use it as effectively as possible. I always say, I know the geochemistry very well, but operators know their acreage much, much better than me. And so when you can combine those, then you can be much more useful in what you deliver. So I am going to very briefly talk about an example from the Midland Basin, specifically from Martin County. And what we have in this project is a mixture of pilot holes with core and cuttings, water-based mud cuttings in most cases, some laterals of oil-based mud cuttings, and then the produced oils themselves. And the overarching objective of the project was to understand where are the fluids being produced from, what is the trend in my acreage, and what can you tell me about perhaps how we should optimize our production and what we should be doing for our next wells. And that tends to be quite often the questions we get asked. And so this is a brief example from a lateral in the Wolfcamp A. And so we have a vertical and we have lateral data. This is TOC on the left and Tmax data on the right. And I've shown vitrinite reflectance equivalents for those who like looking at it that way as well, to give you a sense, although bear in mind that is more of a guide rather than a definitive answer. So what you should take away from these graphs, certainly the one on the left, is there's about 4% TOC variation in the vertical. There is an equal amount of TOC variation in the lateral. So we have significant TOC variability and heterogeneity in our lateral. Furthermore, if you were just dealing with the vertical, because those are the only extracts you can get access to, because the lateral is using oil-based mud, then you are not getting or capturing a sense of that heterogeneity from your extracts when you are going to allocate your fluids. The same story applies to the maturity variation on the right-hand side. As we move along depth, the maturity is decreasing. Okay, it's changing from a Tmax of 447 to say 438. It's not huge, but it is certainly significant. And we see the same trend in the laterals in the adjacent target zones because it ties up with the trend in maturity in their acreage in general. But that has an implication for when you're trying to do, say, comparisons between biomarker maturity in the rock extracts in the pilot hole relative to perhaps from the oils in the laterals, or even any geochemistry in the pilot hole relative to laterals. If we have significant variation in our lateral, but we're not capturing that in our extracts, I mean, and it would be difficult to do so as is, then what are we talking about when we're talking about allocation? So if we take some cuttings drilled with water-based mud through the stratigraphy, And we have a whole bunch of oils, which are our circles from the Wolfcamp A, the Wolfcamp B, and the Lower Sprayberry. What we see is that actually maturity tends to separate out our different zones much more readily, and I've actually seen that in the Midland Basin quite often. And I would emphasize that if I gave a 3-hour talk, I would show you a whole range of statistics and geochemical data, but in a 10-minute talk, I can only make you just slightly dangerous at geochemistry. But what this suggests is, and from the rest of the data, the Wolfcamp A and Wolfcamp B oils correlate reasonably well with their associated extracts. So they're generally producing predominantly from those zones. The Lower Sprayberry oils, in contrast, are too mature when compared to the Lower Sprayberry extracts. What they look more like is the extracts from the Dean. The Dean more than likely being higher maturity migrated fluids, and perhaps suggesting that those Lower Sprayberry laterals are primarily producing from the Dean, which is not overly controversial. That's relatively well known with a lot of the wells along the Lower Sprayberry. Why am I not comparing any of this data to the laterals I just showed you? Because I emphasize the laterals are drilled with oil-based mud. Oil-based mud is the enemy of geochemistry. And so if I was trying to use the laterals, all I would be showing you would be geochemistry from the diesel and so forth. So that's why we have to look at the pilot core for this detailed comparative geochemistry. So, I mean, if I wish to, I can deconvolute my fluids. And so we've deconvoluted the Wolfcamp B landed wells. And what we get is around about 66% Wolfcamp B and 33% Wolfcamp A. And these are our mixing curves generated by my colleague, Mark Bastow. And then for our Lower Sprayberry landed wells, they are actually 93% Dean sourced and 7% Lower Sprayberry, which, given our qualitative assessment of the crossplots and the statistics, that matches up quite well. But given the variability evident in the laterals and the pilot wells, which are all in close proximity, would we call this quantitative production allocation? I mean, we can call it production allocation, but given what I've just shown, and this is standard across all of the projects I've worked on and colleagues have, unconventional work is by default semi-quantitative at best, because we can't really get a wonderful handle on what our lateral variability is. Quite often we struggle with what our stratigraphic variability is, especially when it comes to allocation and we have to define single points in space for that deconvolution. So much of this work we've seen has been, you know, this is your deconvolution, but, you know, take it with a pinch of salt in terms of an absolute value. And so this is my last slide. It's really just emphasize that allocation is always the question, and it's powerful, it's useful, but with the variability we have, it's only one deliverable. There's huge value to be had in understanding your subsurface fluid chemistry. Don't focus on one aspect of it to the detriment of all that other information you can use. And I mean, there's a huge amount of semi-quantitative information you can gain and you can tease out. And if you have at least 2 wells within separate production zones, you can define a whole bunch of indices around compartment uniqueness, fluid variability. And I mean, you don't even need core or cuttings to do a lot of that work. I say at least 2 wells. I mean, you can do it with 1 well, but I'm not going to be able to really tell you much. The work of Jason Joeda and colleagues at Conoco, they worked on hundreds of wells, thousands of samples, and they put together a vast amount of information and understanding. But that's because they have lots and lots of data to work with. And even still, you're looking at more a semi-quantitative result in your absolute answers there. So there's huge value in the cuttings, core, and produced fluid to build your understanding and to optimize your production. Allocation is just one of those components, and the focus on that can take away from everything else, and it can take away from the actual true complexity of these systems. And that is me. Thanks for listening. I hope that was useful as a 10-minute primer.
That was great. And it's a little bit after the hour, but we have time for questions. So I would welcome anybody to turn on their mics and go ahead and ask a question and join in. We've got a lot in the chat, but not sure if all of those were actually answered.
I don't know. I'm gonna raise my hand here.
Yes.
I have very serious questions to how we can call the source rock, seal, and reservoir. How can we discriminate between all of them in the unconventional? Because there are no reservoir, the typical reservoir in the unconventional, the one we perforate and have a natural flow. So we frack probably a source rock, we frack a seal, and we call it reservoir. How we model this, how we do the parameters of the modeling parameters, assuming this is a reservoir. That's not a reservoir, this is either a seal or a source rock, in unconventional. I don't know if one of your speakers can answer this question. I would be happy to listen.
Yeah, go ahead. That seems like a geochemical question.
I mean, this is not just geochemistry question, that is applied to modeling. It
Mhm.
applies to temperature change, pressure change. If we, in the unconventional, we actually frack a source rock and we call it reservoir. And then we take that parameters, we apply it as a reservoir in the modeling system, the conventional system as a reservoir. How this has happened, how that parameters apply from a tide rock to a reservoir. Or in other word, fracking a source rock and make it reservoir is not feasible for modeling. That's the point I'm trying to make. I don't know if somebody can answer this question.
I'll try. Perhaps we don't need to do modeling.
What do you mean we don't need?
Well, obviously we've been fracking it for the last 15, 20 years and
Yeah, you frack source
fracking the
rock,
source
right?
rock and
Right,
it
and you
can be
call it-
also a reservoir, no?
Well, the first introduction of the whole session was applying modeling, and the speaker say modeling can apply to the conventional and unconventional, while using the same parameters. So you take a solid, non-permeable rock, which is a source rock, and you frack it, and you try to apply the reservoir modeling in the conventional to the unconventional. It's completely different lithology, different petrophysics. But anyway, I don't know if somebody can answer my question. Well, probably my question is not.
Hey, Salim, it's Andy Pepper here. Can you hear me?
Yes. Yeah, Mr.
Yeah.
Pepper, how are you?
I'm doing very well. Everybody else, I hope.
You spice everything. Go ahead.
Well, look, it's a hell of a question, but I mean, really, the simple answer is that it's absolutely no different to conventional system. You have variations in capillary entry pressure; those determine the storage. So, in a conventional system, we have this kind of binary difference between a reservoir and a seal. Those differences are still there in a shale,
Right.
Except that they're just on a finer grained, on a more layered, finer basis. So it's all the same. It's exactly the same. It's easy to do.
Yeah, but Andrew, that there are no hydrodynamic in the source rock. The source rock, the hydrodynamic in it is very, very slow. I mean, you expel the hydrocarbon from the source rock probably in 10, 15 million years. But when you drill a well and you hit the reservoir, which is the sand or the permeable bed between the source rock, you produce it right away because it has a flow. But the source rock does not have a flow. And
Well, it does.
modeling,
It has a pore, a finite permeability, and it has a pore system. So the fractures are connecting. They're creating an enormous surface area against which you can draw down small amounts of oil into, you know, from this finer grain. But I mean, really, the question deserves. I mean, I actually run a class for 4 days. If you want to, you know, an answer to your question, but I'm trying to give you a quick answer, but it's you know, we're not going to get there in 15 minutes.
yeah, that's right. I don't want to go through the discussion between, but that's okay. Well, I appreciate your quick answer, but still we need to think about it.
I try to think about it all the time, so I
Okay,
agree
good.
with you on that.
All right.
We'll
All
have
right,
some
thanks.
follow-up.
Thank you so much. Thank you, Susan. How are you? Nice to see you again.
Thank you.
All right.
Nice to see you. Well, I think we'll have some follow-ups because this does bring up a lot of questions, and especially in I'm thinking taking a little bit further in reservoir modeling and simulation.
Now we call it reservoir. It's not a reservoir. The reservoir definition, permeability, porosity, fluid movement. That's the reservoir. So
Well,
we
and
drill.
then we're expanding that now with the transition. So reservoir applies to, you know, water capacity for, you know, and also heat flow. Super
Yeah, going back to Andy, it still has permeability. It's not zero. It just flows too slow, so you have to frack it to help it.
That's right. When you frack it, you just pull fluid from the perimeter just around the borehole. This is it. You cannot pull fluid from half a mile or 500 feet. Whatever you frack, the depth of the frack, 20
Yeah,
feet.
but that's why we do
10
laterals, you know, 10,000 feet laterals to help.
Yeah, the well is lateral, yeah. But the flow is not extended to the limits of the reservoir or the, let's call it the source rock. Anyway, it's very complex. I'm trying to answer it again. I mean, myself, I can't sleep, man. I can just look at it and look at it. I can't find an answer for it.
And that's good. And Craig Berry's put an response in the chat box, which is pretty cool.
Mainly to
Yeah.
Zhiyong.
Anyway,
Thanks,
well,
Craig.
these are great. We'll have time for one quick little question. Anybody else has any thoughts? We had a good turnout today.
Just to wrap up, if anybody has question, please follow up with the speakers, or you can always send us an email to it. And just to let you know, actually, there is the technical interest group. You'll be able to find actually a web page under AAPG's website. So please reach out to us. I know actually 10 minutes is probably not enough to go in depth in these topics. But again, the goal of this particular session was not to dive deep into the topic, just to give a flavor for it so that we can start the interest levels, and probably down the road, hopefully we'll be able to bring some detailed talks in December and hopefully next year onwards. So if you are not, if you're looking for actually a very in-depth presentation, so look out for those, which will be announced shortly. So that's what, and I'd really like to thank all the speakers for preparing actually some materials to share with the entire community. So that's just great. I'll try to answer one question I saw actually on the chat box, and anybody are welcome to correct me. So there is a question like, why there is a few information of offshore shale oil gas exploration. My initial hunch is if these are really tight rocks, obviously permeability, as we are discussing, plays a key role. So obviously the economics and environmental factors needs to be considered. So that's why one of the reason actually there is probably not much of shale gas or oil exploration happening in the deep water settings. But and at the same time, actually, a lot of those, in order to have reached the maturity window, you need to heat enough the source rock enough to expel it. So if it's really deep, it's probably actually reaching in some of these basins to the HPHT condition. So probably there are some drilling challenges. So that's why most of this offshore we are looking at is probably a conventional petroleum systems rather than more of an unconventional system.
Thank you.
So there is one question I saw, actually there is a hand raised up, so you can unmute if you have any questions.
Yeah, good evening, everyone. Thank you for this wonderful presentation. My name is Rokiba Kobi. I'm a student, geology student of Federal University of Technology here in Nigeria. So my first question is to Mr. Sumit. What advice do you have for students with ambition in petroleum geology? And what advice do you have for science students with no programming skill, but have interest in learning artificial intelligence and machine learning? And my last question to Mr. Jim Murray, apart from artificial intelligence and machine learning, what other software can you recommend for students to learn before transitioning from academic into the industry? Thank you so much.
Okay, Rakib. I think I know actually I don't have actually a particular programming background, but there are actually resources on the websites, and there are actually a lot of online courses that you can take, like Coursera or so on, where you can learn actually a little bit of programming and use it to apply to geoscience or any other disciplines. And there are programs, especially in the world of Python, which is actually evolving every single day. So you can check out some of those courses by different academic institutions, which are actually not class-based. You can do it actually over the web. So I would highly encourage you to look at those and get probably an understanding of some of those programming if you really have a passion to do it. Now, I'll be very honest, I'm a geoscientist. I can really do well addition, subtraction, multiplication, and division. So those are my key strengths. So if there is somebody extremely good with programming background, please reach out to Rakib for his question.
Yeah, and this is true, Sumit, that there are many resources available online. And I do agree that Python is certainly a good programming language to focus on, specifically in the field of machine learning. Yeah, I absolutely concur with what you said.
Thank you very much. Well, these were good, and thank you for staying after to be able to listen and share questions and answers. And want to thank our presenters again for being here. It was fantastic, and thank you for giving this like rapid overview of really important information about petroleum systems. And this is just the beginning of the TIG. So thank you again, and want to encourage you again to renew or join AAPG and join us next time.
Thank you, Susan, and thanks
Thank you.
everybody for joining the session.